All right, 7.2, inverses of functions. There's a neat little website right here where somebody has created a GeoGebra kind of an animation to where you can see all the parent function and what their inverses look like. So I kind of thought I'd throw that up there in case you wanted to play with it. But we've used this word inverse several times in algebra. You know, normally we talk about the inverse being the opposite. So, you know, the inverses are like addition and subtraction. We have multiplication with division. We have, when you square something like x to the squared, you know, the inverse of that would be to square root something. So it's something that undoes something else. We have what's called the additive inverse. So let's say I have a number like 3. The additive inverse would be -3. The multiplicative inverse is also known as the reciprocal. So if you start with a number like 5, the multiplicative inverse is 1/5. So those are some things we've used early on in algebra. But to graph the inverse relation of a function, which you're going to have to do in your homework today, you can reflect every point across the line y equals x. Now remember what this line looks like. It's pretty important since we're going to be reflecting over it. Y equals x is this line that runs right here on a 45-degree angle. All right? So you have a 45-degree angle there. And it's basically where when you make the table, you know, every single x-coordinate is the exact same as the y-coordinate. 1, 1, 2, 2, 3, 3, so on and so forth. So that's going to be our fold line, or our reflection line. It also says this is the same thing as switching, so this is pretty important here, switching the x and y values in every ordered pair of the relation. So let's do an example, kind of wrap our heads around this. So example 1 says graph the relation and connect the points, then graph the inverse, identify the domain and range of each relation. So this is our relation. We don't know if it's a function or not. It may not pass the function test, but it's a relationship. When x is 0, y is 2. Put that on there. When x is 1, we're at 4. 2, 5. 4, 6. And then 7, 8. Now, I could try to make it smooth with a curve, or I'm just actually going to just connect it with lines. Kind of have the slope is changing throughout this whole thing. I could have did it smooth with a curve, but I went ahead and did it with a line. Well, now, if I want to do the inverse, so to graph the inverse, I'm going to make a new table. And this inverse, we write it as f -1 of x. All right, that represents the inverse. It's not like a negative power or anything like that. That's just notation for the inverse of something. Well, I'm going to reflect all these points and just switch the x and the y's. So instead of 0, 2, I'm going to have 2, 0, 4, 1, 5, 2, 6, 4, and 7, 8. Which it looks like my last point up here was 7, 8. I think excuse me, I did it backwards. When x was 4, 6, that one looks good. This one does not look good. This point needed to be at over 7, or over 8 up 7. Actually, right there. There we go. So here are our points locked in from the original function. So this one up here, this is the function f of x. Well, now we're going to do the function f -1 of x. So go over 2 up 0, over 4 up 1, over 5 up 2, over 6 up 4, and then over 7 up 8. All right, and now when I connect these points, they kind of converge on each other. And you will notice the symmetry in this graph. You know, think back to that line that we were talking about, that line y equals x, that cuts through on a 45-degree angle every single one of these corners right here. And you will notice that that's the fold line. That's the reflection line. So anytime you have a graph and you have its inverse, they're going to be symmetrical like that. So this was f of x. This is f negative 1 of x. All right. Now it says when a relation is also a function, you can write the inverse as of f of x as, so I already just talked about that. But you can only do that when it's a function. So luckily the one up above was a function because there was no x that mapped to two different y's. So we were in pretty good shape. I was safe to use that. And then kind of what I said before, it does not indicate the reciprocal. So don't think of it that way. Functions that undo each other are inverses. We've talked about that. That's the add, subtract. Basically in algebra, it's what you're doing to both sides. You know, when you think about solving an equation, you know, if I were to say, hey, solve 3x plus 5 equals, I don't know, 16. What you want to do is you're trying to undo all of this stuff here. So when I look at it, like I have a times and a plus. So to undo that, I'm going to be subtracting from both sides, and then I'm going to be dividing from both sides. All right, that's kind of our algebra moves. We've been doing the inverse all along to try to solve that. So it says use inverse operations to write the inverse of x divided by 4 minus 5. Well, so think about this. So if this is f of x, and I were to give you an input to put in, and I was to say, hey, you know, stick 4 in there. What you were going to do, your very first step, you would divide by 4. And then your second step is you would subtract 5, right? So for instance, if I said, hey, you know, what is f of 4? When you stick 4 in there, you would do 4 divided by 4, get an answer, and then you would subtract 5, and you would get an answer of negative 4. All right, so this is just straight up as it is. Well, if I want to do the inverse of that, I want to do everything opposite and in the reverse order. So to do the inverse of that, I want to take my starting number, and instead of dividing by 4 and then subtracting by 5, I'm going to do the reverse order. All right, the reverse order would be to add 5 and then multiply by 4. So I'm going to add 5 to this, and then whatever that answer is, I'm going to multiply by 4. So I think that I've found the inverse just by doing the operations backwards. And the only way to know for sure would be to graph these two. So let's just kind of do a little quick and dirty graph here. If I make a quick little table for these values, and I could have did this on a graphing calculator, probably would have been faster. Maybe I'll do that. Let's just fire up the old graphing calculator and let's graph these two, see what shakes out. And whenever I graph inverses, I want to start off by putting y equals x on there, because that's going to be our comparison line to see if it's symmetrical like it's supposed to. So I put y equals x, and I'm going to put y equals parentheses x divided by 4, subtract 5, slap that dude in there. And then the inverse that I came up with was 4 times parentheses x plus 5. And we're going to test this and see if it works. Let's make sure we're at a standard window. No, we're not. Must have been doing some crazy problem. Standard window. There's y equals x. There's f of x. And there is my my inverse of f of x. So it looks to me like they're symmetrical. Now it looks a little bit weird, and that's because my window is a rectangle, so it's skewed a little bit. If you want to fix that, go to zoom and go to z square. You see number 5? That forces the screen to be like a square. And now I think we'll see a little bit better symmetrical, where everything is kind of not distorted or stretched horizontally. All right, good deal. That was faster than doing it by hand anyway. Now, Probably what you're going to use most, though. That time I was just trying to think in my head the operations and do it backwards. More importantly, as we get further on, you can also find the inverse by switching the x and y in the original function and then resolving it for y. All right? So here's what we're going to do. We want to find the inverse of 2/3 x plus 2. So what I'm going to do is, here's the original equation. Y is 2/3 x plus 2. So this is the original. And what I'm going to do now is I'm going to switch x and y. So I'm going to put my x here. I'm going to put my y here. And now I need to resolve for y. So let's resolve for y. So the first thing I'm going to do to get y by itself is I'm going to subtract 2 from both sides. And then to get rid of that 2/3, I'm going to multiply by the reciprocal. So I'm going to multiply by 3/2 to both sides. And these will go away. And now I get y equals, and if I distribute there, that's going to be 3/2 x minus, what would that be? 6 divided by 2 would be 3. So what we've just done is we've just created the inverse function. And we could graph those on the graph. You know, these are both in slope-intercept form, so they're not too bad. So it has a y-intercept. I'm doing this one right here, the original. Y-intercept at 2. Well, let's just do another point here. An easy point might be, I don't know, maybe when x is 6. When x is 6, that's 12 divided by 3, which is 4. So it looks like 6, 6 is a point on the graph. And the slope's basically up 2/3, up 2/3, up 2/3. So I could just graph it using slope. It'd be a hell of a lot faster. So we got that going on. Let me bust out my ruler here so it looks good. Everything looks beautiful. All right. So this is f of x. That's our OG. That's our original. Now we're going to do the inverse. What happened when we switched x and y? Well, that one crosses at a -3. So that one crosses down here at -3. And it goes up 3/2. Up 3/2. So up 3/2. Up 3/2. Up 3/2. Up 3/2. And I'm going to graph this one. So there is the inverse of f of x. And now we need to compare it to our friend, the old line y equals x. Oops, fell off my ruler a little bit. And it looks good. It definitely looks like it's symmetrical. So we always use that line y equals x to test to see if the points did get, flipped around. And we can see that. You can see that this point right here, which is at 4, 3, the other line is at 3, 4. 2, 0, 0, 2. Here they actually are the same. They're right on the line. We see another reflection up here. So it definitely worked algebraically. So that's the algebra way to do it without just trying to kind of think about all the inverses. Here's kind of an application. So it says a clerk needs to price a digital camera that was returned by a customer. The customer paid a total of $103.14. So this was out the door, $103.14. So I'm going to write that down. $103.14. That was the finishing price. That included a gift wrapping charge of $3 and then 8% sales tax. And it says, what was the original price? So we don't know the original price. Well, when I walked in the store, something was the original price. And then they added a $3 gift wrapping charge. And after that gift wrapping charge, they applied sales tax, which is 1.08. Okay? 1 gives you the price of what you started with, and then the 0.08 represents the tax. So that's how I would calculate it. So if I wanted to find the original price, all right, if I want to find the original price here, I'm just going to undo everything that was done. All right, so if I wanted to kind of do it fancy, I could say, hey, take the price of the object, add 3, multiply it by 1.08, and that will give me the cost. Well, I could switch those two variables and solve for it. So I could switch these two variables out and say C plus 3 times 1.08. Maybe I'll just, don't need to put it in parentheses. Equals P. So this was the switch part. And then I could just resolve it. Now this problem didn't tell me to do that. I could have just solved for P over there. But I'm just kind of showing you if you started with a function. So the very first thing I would do is I would divide both sides by 1.08 to solve for C. So I'd divide by 1.08, divide by 1.08. So that's gone. Then the next thing I'm going to do is I'm going to subtract 3 from both sides. Subtract 3, and I would come up with a new function that could be used to go backwards and find the price. Now what I would do in this real life problem over here is I would just start doing the inverse. I'd divide by 1.08. Let's just see what shakes out on that one. I am at 103.14 divided by 1.08. Enter. So this is $95.50. And over here I just have P plus 3. And then my last move will be minus 3 from both sides. And I find out the original price is $92.50. And if you wanted to check it out and just see if it works, you're like, all right, I had $92.50. They gift wrapped it for me. Then I multiply by 1.08. And you should see that it does come out to be 103.14. So the biggest idea, I think there's 2 key points to take away from today's lesson. Let me just kind of jot those down. Right down here. Two key takeaways are, number 1, the inverse is the reflection. If I could spell reflection. The inverse is the reflection of a function over the line y equals x. Okay. Basically, that in a table, if you have a table, you can flip-flop all of the coordinates to get the inverse. So that's kind of graphically. And number 2, you can find the inverse by switching x and y and solving for y. Those are the 2 biggest takeaways that you want to kind of leave this thing with. All right, hopefully that's enough to get you through the practice on 7-2. You might run into some, some nastier things or some little nuances that, you're only going to find out if you try to tackle a bunch of problems and ask for help in class. See you.